Hello and welcome back to lesson 6.3. I hope that these videos are going well for you guys. You'll have to let me know what you think. Today we are going to talk about nth roots. You can see here nth roots and rational exponents. So first we're going to talk about the fact that you guys are pretty familiar with square roots and even cube roots, but we can have fourth roots, fifth roots, sixth roots. We can have any number of roots and could be any power. So if we do have, let's say, a sixth root, if I have negative 2 to the sixth power, then I would say negative 2 is the sixth root of 64. Okay? And the symbol that we use here, whatever number this is, so if it's just a square root, we don't have a number here. We just have the radical symbol. So if it's just a radical symbol, then the index is 2. We don't write the 2. But if it's anything else to the cube root, the fourth root, fifth root, etc., then we'll have a little number here. And then this number inside the radical symbol is our radicand, is what we call our radicand. Now, some numbers have more than one real nth root. For instance, square root of 49 technically has 2 square roots, 7 and negative 7. However, with the square root symbol, that will be the principal square root, which is generally the non-negative or the positive root. So when you see the square root symbol just by itself, or the radical symbol, whatever power that happens, or index it happens to be, we will always take the positive square root, unless you see the negative outside. Then that indicates we want the negative square root, or the opposite of the principal square root. So again, we call 7 here the principal square root. And then if you see both, then we would want both. A few things, when the number inside the square root, so when the radicand is greater than 0 or less than or equal to, we'll look at all these cases, and n is even. So for instance, square roots to the fourth roots to the sixth root versus when n is odd, cube roots, fifth roots, seventh roots, etc. If n is even and the number under the square root is greater than or equal to 0, then again we would have one positive and one negative square root. So like square root of 49, we have positive 7 and negative 7. If the number is less than 0, square root of negative 49, you guys know already that those are imaginary numbers. They don't have a real root. And then the square root of 0, or the cube root, or any root of 0 is always just 0. Now, if the degree, it's not the degree, but the index is odd, then there will always only be 1. So for instance, the cube root of 8 is just 2. 2 times 2 times 2 is 8, but the cube root of negative 8 is negative 2. So you can take odd roots of negative numbers, and there will always only be one value, because again, a negative times a negative times a negative is negative, a positive times a positive times a positive is positive, so on and so forth. So when we want to find roots of values, and again, we won't just have numbers, but we'll have expressions. This indicates we want both the positive and negative roots. So again, what is the square root of 25x to the fourth? Well, again, the square root of 25 is 5. The square root of x to the fourth would be x squared. So again, what are we squaring here? 5x squared times 5x squared equals 25x to the fourth. So the square root of that would be 5x squared. Now when we have higher powers, just be careful here. This one we want the negative square root. So the square root of y squared plus 7 to the 12th, the negative will keep outside, and then the square root of this would be y squared plus 7 to the 6th, because if I multiply this by itself, remember, anything this to the 6th times this to the 6th, again, we add the exponents. So really, when you have an exponent, you could just divide it by 2 to figure out what comes outside the square root. Here, this is a cube root. So the cube root of, let's see if I can get this to work. The cube root of 343, you can use your calculator if you don't know your cube roots, or it might be helpful to keep a list of cubes. 1 cubed is 1, 2 cubed is 8. So just kind of keep a running list of perfect cubes. But the cube root of 343 is 7. So we can take the cube root of 343, and then the cube root of a to the 18th, again, we can just divide that 18 by 3, because if you think about it, a to the 6th times a to the 6th times a to the 6th. What do we do with all those exponents? We add them together to get a to the 18th. And then so same thing here, b to the 6th, just divide that exponent by 3, and we'll get b squared. So the cube root, since 343 is positive, this is positive 7a to the 6th, b to the 2nd. And here, square root of negative 289, that's not a real number. However, we do know imaginary numbers, so we can say that the square root of negative 289 is 17i. Also negative 17i, but again, we only have the principal square root symbol, so we'll use 17i. And then c to the 8th, 8 divided by 2 is 4, 4 divided by 2 is 2, so we can write the square root of that as 17i, c to the 4th, d to the 2nd. Now sometimes with even roots, okay, so if we have an even root of an even power and the result is an odd power, then we have to use absolute value to ensure that the answer is non-negative. For instance, we can't take the fourth root of an odd, of a negative number. This should be a positive value, but when I take the fourth root of this, the fourth root of 81 is 3, because 3 times 3 times 3 times 3 is 81. X to the fourth root of that would just be x. So because x can be any number, we want x to be positive, so we'll use absolute value symbols here. And again, that's only when we have an even root of an even power and the result is odd, then we will just put absolute value here. So here, the 8th root of 256 is 2, 24 divided by 8 is 3, so this is an even root, even power, odd result. So we'll use absolute value here to ensure that this value is positive, because we want our principal square root, and the principal square root is always positive. So that's just one quick thing to note. Only in this situation do you have to worry about that. Now the other thing we're going to look at are rational exponents. So I don't know if you guys have learned this yet, but the square root of x, I don't know if you've known, is the same as x to the 1/2. So I don't think we've talked about that, but maybe you've talked about in other classes, that the square root of x and x to the 1/2 really mean the same thing, because if you think about it, x to the 1/2 squared equals just x. If I square this, I get just x. So we are going to work on changing things from exponential form to radical form. It's an exponential form if we have an exponent, and radical form if it has the radical symbol. But for any integer, b or n, and then real number b, b to the 1/n is the same as the nth root of b. So for instance, 125 to the 1/3 is the same as the cube root of 125. Negative 49 to the 1/2 is the same as the square root of negative 49. Now, the fraction might not always have a 1 on top, so for any other integer value, then we can rewrite it as b to the x power and then take the y root of that. So for instance, 125 to the 2/3 is, this bottom number is the index, okay, so it's the cube root of 125 squared. Negative 49 to the 3/2 is the square root of negative 49 cubed, and we can write it like this and evaluate it that way. An expression with rational exponents is in simplest form when all of these conditions are met. There are no negative exponents. There are no exponents that are not positive integers in the denominator. It's not a complex fraction. And the index of any remaining radical is the least number possible. Now let's look at some problems that you're going to have to do here. First of all, writing it in radical form. So if I have x to the 4/3, I can rewrite that as x to the 4th and then the cube root of that. If I want to rewrite this in exponential form, then this would be x to the 2/5. So you just have to understand how to go back and forth. If I have x to the 2/5, then that is, that's just what we just did. If we have x to the 3/4, let's say, then that would be the 4th root of x cubed. Okay, and then if we have the 6th root of x to the 7th, then that is x to the 7/6. So whatever root it is, that's the number on bottom, and then the exponent is the number on top. So you'll have to work on changing some back and forth. I'm trying to go quickly here. This video is going a little bit longer than your last ones. Let's see. So then you're going to evaluate some expressions. Let's see what I want to do. Actually, so you're going to use these exponents and roots to solve equations. We can use it to solve equations. The expression, actually I'm going to save this one for class. That way we don't take too long in the video. We'll save that one for class. Let's look at this next one. If I want to evaluate something with rational exponents, then again, the way we would rewrite this is 64 to the 6th power, or excuse me, the 6th root, but that's actually negative, so that's a negative exponent. So excuse me, first we're going to rewrite that as 1/64 to the 1/6. Sorry about that. So negative exponents, we would write it as 1/64 to the 1/6, and then that will be 1/the 6th root of 64. So now what is the 6th root of 64? Again, you can use calculators, or you can realize that 2 times 2 times 2 times 2 times 2, 2 times 2 times 2 times 2 times 2 times 2 is 64. So the 6th root of 64 is just 2. So this will equal 1/2. So yeah, look for that negative. Sorry, I missed that. I almost missed that at first. The 8th root, or 8 to the 4/3, would be 8 to the 4th, the cube root of that. So there's a few ways we can do this. We can actually write this as the cube root of 8 to the 4th power as well. So you can write this either way. They both mean the same thing. And this one will actually be easier to evaluate. So the cube root of 8, so the 4 can go here, or it can be outside of the exponent, or outside of the radical. So the cube root of 8 is 2, and then 2 to the 4th power is 16. So that'll be easier than doing 8 to the 4th and then taking the cube root of that. You'll get the same result. This way is just a little bit easier to evaluate. And then again, same thing with this last one. We have a negative exponent, so that's 1/32 to the 2/5. Now this one, again, there's several ways we can do this. We can rewrite this as a radical, or if you recognize that 32 is 2 to the 5th, then it's 2 to the 5th to the 2/5 power. And when we raise a power to a power, we just multiply the exponent. So that's another way we can do this there. Again, there are several different ways, and we'll work through some in class together. If we want to simplify expressions with exponents, x to the 2/3 times x to the 1/6, same thing we do if it was x squared times x to the 3rd. We would add the exponents together. So even if they're rational, if they're fractions, we still use those same properties of exponents. So we're just going to add 2/3 plus 1/6, which when we add those we get 5/6. Y to the negative 2/3 is 1/y to the 2/3 power. Okay. Now, we are going to talk about rationalizing our expressions. We won't do that with this one right now, but there is, the book wants you to rationalize your denominators, which means you wouldn't have any radicals in the denominator, and again, that's something we'll come back to. For this last one, again, z to the negative 1/3, z to the 3/4, we need to add the exponents together. And if we do that, we get z to the 5/12. So those same rules of exponents apply whether they are fractions, rational exponents, or just integers. And that is where we will stop for today. We will work on this in class tomorrow and talk about solving equations using those rational exponents as well. All right, see you soon.